This is the very simple network that we are going to learn how the back propagation happens. We have input layer, we have output layer, and we have hidden layer. The input layer, it can be any number, but we have the variable x1, x2, and x3. In the hidden layer, we have two nodes, node number 4 and node number 5. In the output layer, we have one node. For every node, we have the bias and another bias. So this initial input is given, the initial weight is given, and the initial bias is given. So this information, if you can see, the x1 will be 1, x2 will be 0, x3 will be 1. So this is started with 1, 0, and 1. And then we are going to look at the details for every weight. So you can see for every weight here, weight 1, 4. It means W 1, 4. It is 0.2. And then we have weight 1, 5 here. It is minus 0.2 and so on. Usually this this weight is randomly generated. Random means any number is generated. So we have W14, W15, W24, W25, W34, W35, and W46, W56. And every number is set up here. For the bias, we have the theta, okay, theta 4, theta 5, and theta 6. The final output will be the probability of being class 1. It means if the probability is high, let's say the probability is 0.6, then I can say that it is closer to class 1. Okay. If you still remember, if we have one node, it means it is binary classification. So it can be a binary classification, can be okay. So if only one node, it can be a binary classification, or it can be regression. You still remember what is regression? What is binary classification? Binary classification means we have a classification approach. So the label is categorical. And there are two values, yes, no, by, not by, defect, not defect, and so on. If it is regression, then it is a label for continuous data. Okay. Label with continuous data means I will check the output based on the error. Now, you can look at the final node. It is one node, and this is also one node. So how do we know that it is classification? How do we know that it is classification? Is from the word class. So it is the probability of being class 1. If there is only one node like this one, it means binary. And if we know binary, it has two values, 0 or 1. If the probability is higher than 0.5, so this is just a common sense. If the probability is high, we can say it is more likely the class number 1. But if the probability is less than 0.5, it is more likely class 0. So there are two class 0. Now, with this network, how can we apply the back propagation? We start with the input 1 and 0 and 1. This is the initial input. Now we put the weight on every of this one. Okay. After you have this information, now we can do the first step is the forward, or we call it the feed forward neural network. We go from the input layer to the output layer. The first step is to calculate on every of this node, on this node. Now let's just use the first one. Okay. We will start from this and we want to check what is the result in the node number 4. The node number 4, it means we need to calculate the weight from 1 to 4, weight from 2 to 4, and then weight from 3 to 4. And then we also need to consider the bias. Okay. There are some activation function. For this example, let me use sigmoid or logistic activation function. If you still remember, in some parts before this material, before this page, you can see this kind of forward neural network. We start from the input and then we will do the multiplication with the weight for every input, and then we will do the sigma, or we call it, this is the weighted sum, and we will add with the bias. After that, we will do the activation function. Okay, so this is the step. Then first, let's do with the weighted sum mechanism. In the weighted sum mechanism, so I can just calculate this on 1 is the input, multiply by the weight, which is 0.2. And then plus 0 multiplied by 0.4. Multiply by 0.4. Plus 1 multiply minus 0.1. Okay. So you can look at this formula. We have a bias, so we will add minus 0.4. Then the overall of the weighted sum, okay, the weighted sum, now it is minus 0.7. After we have the weighted sum plus the bias, now let's consider the activation function, and this activation function is the sigmoid or logistic activation function. In the sigmoid or logistic activation function, the formula is this one. OJ equals to 1 divided by 1 plus E. E is a number, okay? The exponential number with the power of minus ij. So minus ij means the result after you calculate with this one. So it means I want to include the minus 0.7. Then the formula will be 1 divided by 1 plus E power of minus ij. So what is ij? Ij is minus 0.7. So it means minus of minus 0.7. Minus and minus, then it becomes positive. So you will see it will be 1 divided by 1 plus E power of 0.7. Then the result is 0.333. And you put that the output in this node is 0.332. After you do the same with the node number 5, you can get the value 0.525. So how do we do the calculation? It's the same. We can find the weight on every node. So it is 1 multiplied by minus 0.3 plus 0 multiplied by 0.1 plus 1 multiplied 0.2, and then don't forget plus the bias, which is 0.2. So the result is 0.1. This is 0.1. Now we again need to use the sigmoid function. The sigmoid function means this is 1 divided by 1 plus E power of minus input. So here the input is 0.1, then it will be minus 0.1. The result is 0.525. Then we will use this one as the output from the previous layer. Now, we can calculate the next layer. How can we calculate this one? The layer in the output or the node 6, it is from the node 4 and then node 5, and then we have the bias. So we can just apply minus 0.3 multiplied by the value, which is 0.332, plus minus 0.2 multiplied by 0.525, plus the 0.1. Okay, the result of this one is minus 0.105. Then we will do again the sigmoid function, and we got the value is 0.474. Okay. So after we have this one, this is the probability. It is the probability of being class 1. If you look at this probability, Is it more on the class 1 or 0? Is it to class 0 or 1? Because the value here is less than 0.5. Then we can say it is more likely, it is maybe it is more on the class 0. So we need to check. If I have this data, usually we have this data like the input is x1, the input is x2, the input is x3, and then what is y? So when x1 is 1, the x2 is 0, and the x3 is 1. So you can know the actual, let's suppose it is 1. Okay, for example, it is 1. But the y prediction, okay, here, the y prediction, it shows it is closely to 0. So it is closely to 0. It means the prediction and the actual is different. In order to make it the same with the actual, we want to learn, we want to adjust the weight, or we want to change this property, how to make the best weight so the prediction result is closer to 1. So we need to improve this. We need to improve this number. Then we can find the error. So this error, we try to look at the value as I mentioned to you. If we have the x1, x2, x3, and then the actual y. Let's suppose if the x1 is 1, if the x2 is 0, and if the x3 is 1, the actual is 1. Okay. If the if the y is 1, we want to know how big is the error by using this formula. So this is the formula in the backpropagation. OJ multiplied by 1 minus OJ multiplied by TJ minus OJ. Okay. What does it mean? OJ means the output given by the network. And we would like to multiply with 1 minus OJ. So OJ is the output of the network. And then TJ. So the TJ means this is the target. As I mentioned to you, x2, x3, we have the y. The actual value is 1. This is 1, this is 0, this is 1. If I know that this is 1, then we put it, the TJ equals to 1. Maybe if we have another example, let's say 0, 0, 1, for example, and then the actual is 0. Then with this input, we will consider this as the TJ. So the TJ will be 0. But now let's say this is 1. Because it is 1, I would like to know how big is the difference from the class 1 and the output. So 1 minus 0.474. The result is this one. So the error is 0.1311. After I have this, now I would like to back propagate. Back propagate. It means I want to return to the previous node. I want to go back to the previous node, and I would like to check every error. I want to calculate the error. The previous one, we calculate this error because this is the output layer. Okay, you can look at the algorithm here. So if it is the output layer, okay, if it is the output layer, then you need to compute with the formula in the line 12. But if it is in the hidden layer, you need to compute with the error rate in the line 14. Okay. So this is the error rate in the output layer. And you will do the calculation in the each layer. How we do this calculation? You will see the output multiplied by 1 minus the output, and then we will do the error multiplied by W. How can we make this one? First, you know the output. Let's say this one. What is the output? The output is the red color, 0.525. So this is the output. And we will subtract 1 minus the output, 0.525. This is a summation of the error rate of K multiplied by WJK. What is this error? This error means the error that has been calculated in the layer in one step after this layer. So it means this error rate will affect this error. So I would like to check how big is the error rate according to the error rate in the next layer. So we have the 0.1311 from the previous layer multiplied by the weight. This is the weight based on the weight from the node 5 to 6. We have this formula, and then we will have this result. So why do we have this sigma? We have only one node after this layer. Then we have only one. But if there are multiple nodes, for example, let's say this is a node, and this node has the output in two different layers. So you need to do the summation. Now the same with the node number 4. In the node number 4, we calculate based on the output. The output is 0.332, this is the red color, and then 1 minus 0.332, and then we will multiply with the error rate in the advanced layer, which is the output layer, multiply by the weight between the node 4 and node 6. So we get the value is minus 0.0087. So the green color is the error, and This one also. After we have the error, we can we have this error on the node 6, we have the error on the node 4, and we have the error on the node 5. So we can update. We can update the weights and we can update the bias. What is the meaning by update the bias and update the weights? If we want to update the weights, it means this one. I want to update the weight. Why? Better predictions means lower error. Okay. So we want to make the model which is the lowest error. Before, you can see that the output shows 0.4 something something. Meanwhile, in order to predict that it is 1, the error rate is still high. That's what we can do with the back propagation. Let's try to update the weights, and hopefully by updating this weight, the result might be closer to 1. Now the error rate is quite high based on the calculation. Based on this calculation, the error rate is 0.1311. We need to reduce it until the least error, and then we will use that one. So there is an opportunity to update the weights, and this is the calculation. The delta. Okay, delta means the difference. The difference weight between I and J equals to L. What is L? L is learning rate. I already mentioned to you in the last lecture. We have the learning rate. Okay. So if the learning rate is high, what happens? We worry with the overshooting. If the learning rate is very low, it will take a lot of time to do the calculation. So we need to have the proper value of the learning rate. Usually, like I mentioned to you. Okay. So here it mentioned that usually the learning rate is 0.01. But for this example, I think for just easy calculation, let me use the learning rate. Okay. So you can see here, the learning rate is 0.9. So we have the L. The L is the learning rate multiplied by the error multiplied by the OI. In order to update the weight, now let's see. For the weight for 6, for this weight for 6, it will be the current weight. The current weight, if you look at the previous one, okay, the weight is minus 0.3. So the current weight, which is minus 0.3, this is the current weight, plus the delta Wij. Delta Wij is from this one. Then I can move plus with the 0.9, which is the learning rate. multiply by 0.1311, which is the error. Okay. And then multiply by 0.332, which is the output. The new weight 4 to 6 is minus 261. This is the new weight from the node 4 to 6. What about the weight from 5 to 6? So from 5 to 6, the original weight is minus 0.2. This one is the original weight, minus 0.2. Now I would like to plus with the delta Wij. So this is the calculation. The learning rate is 0.9 multiplied by 0.31311, which is the error on the node 6, and then multiply with the 0.525. So 0.525 is the output on that node. If you look at this one, yeah, this is the output. So the red color is the output. So this is the output. The red color is the output. So we get the new value, which is minus 0.138. And this will be the new width here. And so on. Okay. So you can do with the W14 until W35. Okay, let me try with this W14. W14, what does it mean? I want to update this weight. The original weight is 0.2. Now, after I know the errors, I want to update the weight 0.2 plus the learning rate, which is 0.9, multiplied by, what is it? Minus 0.0087. It is the error. Okay. Multiply by 1. Okay. And we will get the value 0.192. And so on. So this is about the weight. How about the bias? So to update the bias, there's also another formula. In order to update the bias, we have this formula. The delta theta equals to the L multiplied by the error G. So it means I will just use the learning rate. I will just use the learning rate 0.9 multiplied by the error. So this error is from the error in the node 6. It is 0.1311. I will multiply with the learning rate, and this is the initial bias, 0.1. 0.1 is the initial bias here. Okay, so the 0.1 plus 0.9, which is the learning rate, multiplied by 0.1311, which is the output from the node 6. So we will get the value 0.218. This 0.218 will be the new bias for node 6. Okay. we will do again, after we have this updated weight, what should we do next? Again, we will do the feed forward neural network. So we will start again from the input layer and then go to the output layer. So we will again multiply 1 with 0.192 and then plus 0 multiplied by 0.4 and then plus 1 multiplied by minus 0.508 plus the bias, which is minus 0.408. Then we get the value, and then again we do the logistic or the sigmoid function, sigmoid activation function, and so on. So if the result, the output from this weight have a very low error, then we stop. Or if you already do many iterations, for example, if you look at this one, maximum iteration, it means if you already reach 50,000, then stop. Or it depends on how many epochs and other things. You can define those parameters. If you already satisfy all the parameters and conditions until the least error or the lower error, then you can stop the training and you can use the last model. So in the neural network, there are some weaknesses and also there are some strengths. The weakness is long. More layer is more training time. And it requires a number of parameters. So if you have this network, the parameters will be very important to make a good structure. And the number of parameters typically best determined empirically. So you need to adjust some kind of weight or the learning rate and other parameters to make it a better network. And this one, poor interpretability. We cannot explain the model. If you use the decision tree, it is easy. When you have this decision tree, I know that, okay, if the x is less than 30, okay, it goes to the left. If the x is higher than 30, it goes to the right. But in the neural network, there is no way to explain. Even though these days, there's also a topic about the interpretability, and I will teach you in the orange. There's also a feature to explain the neural network. Let me just open the orange. But we still need to have more efforts to interpret the result. The strength is it is high tolerance to noisy data. And it has the ability to classify untrained patterns. So if some data is not in the training data set, then it is possible. Well suited for continuous value inputs and outputs. If you have any categorical data, you need to convert or you need to change to numerical data. And it is successful on the array of real world data. for example, handwritten letters. So it's already show a good result. And the algorithms are inherently parallel. It means you have the backpropagation, you have the feed-forward neural network, and you have also the sigmoid function. So there are so many parameters and formula inside the network, and they can work in parallel. Techniques have recently been developed for the extraction of rules from the trained neural networks. So you know already the word pre-trained. For example, nowadays it is very popular for the LLM, large language model. What is that? Daehyung Ono model. We know about the ChatGPT, or we know about the model BERT and etc. So we have the trained neural network or the pre-trained, and we can just reuse it in order to make a prediction. Yeah, so the neural network, it is a set of connected neurons. So we learn about the input layer, hidden layer, and the output layer. In this slide, we already learned about the basic concept of two neural networks, which is the forward propagation and backward propagation. During the learning phase, the network learns by adjusting the weights. So the weights will be updated, so as to be able to predict the correct class labels of the input. The loss function is a function that tells us how good our neural network for a certain task. And the backpropagation algorithm is the most common learning method and has been successfully applied to a variety of learning tasks. So those are some reference. Now, in this orange, they have a very simple algorithm of neural network. Let's say I'm just using the iris, and then let me just go to the neural network. And you can see here, in this neural network, it shows the neurons in hidden layers. And orange gives 100. What does it mean? If you look at this one, so how many hidden layers? How many nodes in the hidden layers? You have only 2. Okay. But orange set up with 100 neurons in hidden layers. So it means you can set up any numbers. And here you have 100. It means this is only one hidden layer. If you want to set up with another, let's say 50, so it means you will have 2 hidden layers. If you split again with comma, 10, for example, like this, then it means you have 3 hidden layers. Okay. But let's just use only one. The activation function, there are some activation functions. What we learn in this example is using the logistic. The solver, I think, yeah, the default is Adam, and you can see the alpha. It is the lambda. It's the learning rate. So you can also adjust the learning rate. So let's just make this one. Now you can make the prediction. The test score. You can see that, okay, this is the classification accuracy with the cross validation 5 times. Okay. Yeah, you can have different parameters on the neural network. For example, yeah, you can see this is the maximal number of iteration. We have 200. Or you can change with the SGG, and then you can look whether, okay, the classification accuracy is decreasing. Then it means the optimizer also affect the result. Okay, I think the time is up. We'll stop here. Any questions?